Thank you so much, Valley, for the introduction. And yeah, grateful to be here with you all today and talk about our work with ACD in building a small molecule database at Genentech. So I work within analytical research in discovery chemistry. We do a lot of LCMS and NMR and really have this keen focus on the value to research. How do we move a molecule into development as quickly as possible and really take advantage of the data that we have so that we can do more with our data and ultimately with less material, since we are working in that discovery space. And also sort of thinking towards the future, since we are looking at so many compounds, how are we leveraging this data and learning from it so that we can anticipate results in the future and maybe eliminate some of those experimental needs? So again, just sort of honing in on what we're doing within discovery chemistry. We work with medicinal chemists and biologists on project teams, synthesizing lots of different compounds and ligands for the targets that we have in-house in the project teams. Those molecules then move into purification, and those pure compounds come for a QC before being registered into our small molecule compound management system at Genentech. And when we QC those molecules, we do LC-MS of it, the compound seen here on the left with this Q-exactive. And we also run 1D and 2D NMR of all these molecules. And a couple things we're looking for there is purity by LC-MS, and also that the structure is correct with high-res molecular formula confirmation, and also by NMR with some cozy HSQC and proton experiments. And a key aspect to this is that we generally maintain next day turnaround. And for where we are and the analyses that we do, it's really dependent on where that compound is going to move. If it's just going to go into a bioassay to see if it's more potent, has better PK, and if we're really honing in on the different structural features and structure activity relationship that we mean to be, then we'll probably just do LCMS and NMR, get it registered and get it into that assay with 1 day turnaround. And for that analysis, we need about 2 milligrams of material, versus if it's going to be moving into an animal study, we'll likely need 50 milligrams of material, and all the analyses that we're going to perform can take up to 2 weeks. When we are moving in this really rapid turnaround space with LCMS and NMR analysis, we're analyzing about 2,500 to 8,000 compounds a year, whereas these longer studies before moving into animals are generally only around 60 compounds a year. But you can see within this discovery space, we have a lot of data. And so ensuring that we're capturing that data and learning from that data is really important to us, and is what led us to initiate this collaboration with ACD. So in working with ACD, the first thing was just to sort of understand who's going to be using this database, how they want to interact with the database, and how the data should be processed into the database. So ACD has the ability to analyze and process all different types of vendor data. And the automation server automatically sweeps our NMR and LCMS and all our different instruments, pulling that data into the database. That data, it also accesses our internal sort of Oracle small molecule data infrastructure, where we house all of our small molecule data, register that data, track how much material we have, if that data or material is moved into DMPK studies, biochemical studies, safety studies, or where. And it gets all that metadata associated with the data out. So it gets structure, chemist name, project name, all of that is stored internally in our ACD database and is searchable there. Then we do a verify in the ACD database, where it considers alternative structures, everything associated with that data and the structure that we're proposing. It also creates purity tables with our LCMS data and stores all of that and creates all those reports into our database. From there, our group often looks at it, ensures that every impurity that was in that sample is accurately integrated and accounted for. And then a lot of our downstream users also have access to that, and maybe their own GUIs or scripts for interacting with that database. And like I said, since we're really looking at so many different compounds, and we might be moving an oxygen around and building out SAR, and later our downstream colleagues are seeing that as a metabolite from a P450 enzyme or as an oxidation impurity in development when looking at stability of our API. And so having access to dereplicating their data relative to data that's already captured there makes their structure elucidation or metabolite ID much more efficient. And synthetic chemists are always responsible for capturing IP, maybe publishing all that NMR and high-res data in patents or publications, and having an ability to pull per project all of that information out in the format that they need was a really important way for them to be able to interact with the database as well. So early on, they kind of, working with ACD, we were able to put together sort of these user stories and create an infrastructure and scripts and all sorts of different buttons that I'll kind of walk through for everyone to access the database. Like I said, kind of when we were building this out, we had 3 different teams where everyone was giving their input on how they wanted to interact with it. Specifically for chemists, when thinking about patents, like not over-reporting those multiplets is an important feature. For us, the automatic data processing was really important. And for our downstream colleagues in small molecule analytical chemistry working in development, being able to have Marcuse structures that aren't over-assigned, but are very specific to that part of the molecule and localizing, say, this extra oxygen to that area is important. So now I'm just going to kind of walk through our interface as a user of our database and some of my favorite features associated with it. In general, it's pretty straightforward. Lots of different ways you can look at your data. Since this is from one of our thermos, right now you can see we're in Excalibur view. But again, we have a lot of different custom workflows and views that ACD has set up for us based on what we're looking at. On the left, you can see the record navigation panel associated with this molecule. A lot of the processing and metadata below that. You can see we use what's called SMIDI numbers, which are just sort of 8 different numbers, identifications for each compound that we analyze. Project information, chemist name, all of that is stored in there. And on the top right, you can see we also have some custom scripts that they built for us, for our group specifically, since we are doing structure elucidation, and maybe we want to update our prediction database based on what we're analyzing. So all of this was really custom built and easy to navigate based on either scripts or tabs in the way that we want to view the data. A really important feature for us and chemists is having, since they are accessing our internal Oracle database of small molecule data, it gets chemist name and everything. And as a chemist, they really like being able to just search on their name and maybe a specific time period and get all the molecules and the analytical data that they registered in this time period out. And so you could see that here on the left. On the right, we also have G numbers or SMIDI numbers, which is just sort of how we register our small molecules. And if you want, you could just put all of them in there separated by a comma and get all the analytical data out, either in an Excel table or any format that you want. And on the bottom, what I'm highlighting here is how, as a structure elucidation chemist, if we assigned a really nice 2D data set, we have HMBC, carbon, NOSI, like all this 2 and 3D data associated with our compound, and we want to push that into our prediction database to better predict these structures or compound class in the future. We have a specific tool and button just to do that. Other really nice features are we can kind of toggle on and off. Here you can see on the top pane is our chromatogram view, starting with our CAD, because we're getting CAD and UV data of all the compounds that we analyze. Below that, we have our total ion chromatogram, and then an extracted ion chromatogram for the compound that we were analyzing. And we can toggle all those on and off just by clicking them on and off on the left-hand view there. If you want, we could extract new wavelengths, or since we collected PDA data, any extracted wavelength that we want. We can also search the database. You can easily move between drawing in ChemSketch, the database, the processor, all of it. So at any point, we can move data and search by spectral similarity as well. And I kind of also like how when looking at a lot of different compounds, you can look at their UV and mass spectrum, your MS spectra, all of that in the table format as well. And like I said, it's really easy to move between this database, processor, and ChemSketch. And I would say my number one favorite thing about the database is that it is so structure-centric. And so if I want to say, is there anything similar, or do a substructure search on a compound, within ChemSketch, you can specify your database and either do a compound search or an SS or substructure search for a specific region of that molecule to pull everything in your database out and see the raw data associated with it. So when thinking about doing dereplication or sharing project information with people, being able to organize it based on substructure or compound class is incredibly useful for fast dereplication for everyone downstream of us. And another, just the purity table. Again, this is a really important thing, and we have different purity guidelines based on whether it's going into compound management and bioassay, or it's moving into an animal study. So being able to look at these purity tables and all the different reports associated with it is incredibly important, because we want to make sure we're considering all the CAD for any impurities that could be present without a chromophore, and our different impurities present, similar often to the compound that do have a chromophore. And if you want to see any of these individual technique reports, all of those are saved both as PDF, and again, just the raw data if you want to manipulate it within our Spectris records as well. And here's an example of the purity table. And by UV, it looked 100% pure. In CAD, we picked up a couple impurities and saw it was 91% pure. And then we had different purities based on whether we were looking at 220 or 254 nanometers. So again, really easy to just flip through these and see what the actual purity of that compound is. Doing structure elucidation and working with incredibly talented chemists, a lot of times the structure that they want to synthesize is exactly what they make. And I get used to looking at the data with that bias. And one feature of the ACD database that I really appreciate is that we also have it set up that in our database, a part of the verify script is it considers 5 other substructures that maybe as a chemist we haven't considered. And it looks at all your data, predicts the data for each of these other 5 potential compounds, and sees if any of them are potentially a better match to the experimental data. It scores all of those 5 other potential structures and relative to the experimental data, and you can look at that within your NMR report as well. And in this case, our desired compound was the best hit, and everything else, was second to that. So, and here's just an example of our processed NMR reports and HSQC there associated with the structure. And sometimes when we do see like a little bit of ambiguity in another potential substructure, if we just add one more piece of information like an HMBC, we can get that number up to like high 90s again, because there's just a little bit of ambiguity in maybe one of the spin systems. Here's an example of our LC-MS reports, and we have purity tables on the report, our compound, all the chromatograms, and we're also acquiring our MS data at 6 different collision energies. And, you know, as you would expect, the more labile components come off at the lower collision energies, and then we start accessing more of that you know, compound information in the more difficult to fragment regions and those product ions at the higher collision energies. So we're filling our database with all of this rich knowledge at all these different collision energies for these known structures. And a really important part of this, and the way that we saw ourselves collaborating with our downstream colleagues, is the ability to search that MS data relative to the database. And one of my favorite ways to look at this data is through what are called mirror plots. And so you can have your query MS spectrum on the top and a hit MS spectrum on the bottom. And since we are acquiring this on a high resolution accurate mass instrument, each of those is associated with a formula loss. So we can look at where on the structure is that formula loss localized, and then where are these differences. And one such example of that was, again, here's the query MS spectrum on top and a hit on the bottom. And with this, we were able to localize the addition of a methyl group to this one ring, relatively labile, but a clear formula difference of a methyl group between our query spectrum and hit. And also a nice feature, you know, we never want to over-assign things. I'll just go back to that and mention it, because when we're building a database, you know, sometimes you're forced in to draw a structure per spectrum. And within ACD, you can actually have Marcuse structures as the assigned structure with the spectrum. So say if you're in DMPK and you're building up your database that way, and you just have a lot of Marcuse structures, like that's 100% okay. And it's actually incredibly valuable information as well. And important not to overassign that. Like when it is time to localize, where is that methyl group? That's when we move and add more data, like our NMR experiments. So yeah, our database contains a lot of Marcuse structures as well. And yeah, we just want the structure to represent the level of confidence that we also have in that data. And again, our chemists' favorite feature really is the ability to extract out in the format that they need all of their multiplet information, their NMR data, not over-report those multiplets. If it is going into a patent, the associated mass error with the compound and what was the experimental versus theoretical, and all of that is in these tables, or which can easily be exported to Excel and just copied and pasted into the desired either patent or publication. And one thing, you know, when thinking about how are we using our data, what we also really appreciate and understand the value of ACD in predicting what chemical shifts should be for a compound and being able to compare those to our experimental data. And what we found is with certain compound classes, you know, it does a really good job, but there's still some error associated with that. And in my experience, the minute you add one compound from that compound class to your prediction database, it does an incredibly good job at predicting everything after that. And so if we're looking at the same impurity where we had the additional methyl group, it did a pretty good job at predicting, again, we're kind of looking more at the aromatics and stuff associated with this compound. And you can see that here in the ACD original prediction column. And then our experimental data is to the right. But the minute we added that original reference compound to our prediction database, then the ACD predictions are seen here on the right. And you can see they're almost spot on. So in our experience, having this prediction database and as a structural elucidation chemist, being able to add to that, even just one compound representative of that database, of that compound class, has been incredibly enabling for us in annotating our data as well. So, annotating our data, all the data that's going in there is really the value that we're creating in our prediction databases for our department and for all the departments downstream. So the data, the LC-MS-MS at 6 different collision energies and just proton, COSY, and HSQC that we get on all compounds that are synthesized. And we've set those up with non-uniform sampling to be about 15 minutes per compound. And acquiring all of that overnight, auto-processing that data, verifying the spectra, ensuring that it really is the best compound hit for the data, experimental data at hand. And then as we review data or as we create data, updating that prediction database just so that we're getting even better at that as we move forward. And I would say ACD has been doing this on the NMR side of things for a really long time. And I love, on the NMR side of things, if we're looking at some data, we're like, that chemical shift is a little bit off. It's not what I would expect. You can immediately take that zoomed in part of your data, search it relative to the database, just your zoomed in region. And they've recently made the same capability for MS-MS data. We can be zoomed in on that specific part of the MS-MS data and search it because it's kind of unique or maybe something that you think you've seen before and solve for a similar compound. And I think we all know, like, there's a lot of software programs out there, and it's a big push worldwide to create the best algorithm for interpreting MS-MS data. And some of them can be a little wonky in the product ion structures that they propose. And so what we're working on with them right now is, can we take our MS-MS data at these 6 different collision energies? We know the structure, we've confirmed it by NMR, push that into a learning algorithm so that in the future we have more accurate MS-MS annotation of our pure compounds. So that's a current research collaboration we have ongoing with them. And I think just, being able to put high quality data into this database so that as we do move forward and think about ways that we can learn from and utilize this data, we're in a really good place to do that. And so our vision is just within Genentech and globally with Roche, we have a lot of collaboration with them, and they do a lot of downstream small molecule work in collaboration with us. And so thinking about how are we capturing our data, learning from our data, and then our downstream colleagues then do replicating their data as quickly as possible so that whether you've been on this project team and looking at this data for months or you're new to it, our data isn't siloed. Our data is universally available, access, and really easy to use interfaces for everyone who needs to be accessing that data so they can quickly address their project needs. And really reduce those structure elucidation timelines. And we also have this vision that as a project moves from the discovery space into development, we can have these impurity kind of package, or profiles that move with the project so that you can see how did this what was its relative retention time to the API in reverse phase in discovery? How did it fragment at these different collision energies? Like really just build up a lot of that structural information and keep it with the project so that no matter who is touching it, they have this inherent knowledge of the project and the risks and impurities associated with it. And with that, yeah, I just want to say thank you and thanks to everyone at ACD and here at Genentech for the collaboration, because it's been incredibly fruitful, not just for the development work, but they are also thinking about, are we capturing the best possible data, highest quality data? And, we rely on our expertise and their expertise, and collectively, it's been an incredibly fruitful and thoughtful collaboration in what we've been able to create together. So yeah, I'm happy to take any questions y'all have, and thanks.